Right, hi Year 10. So, what we're going to be doing today is we're going to be starting to look at waves. But before we do, as I said, we are going to be going through the test from yesterday. So can you get your answers ready to go? And we will go through that. Apologies in advance because we're going to have to be jumping between the questions and the answers. Okay, so I'll have the questions up like this, but then I'll also show you the answers. So, the drag lift pulls a skier from the bottom to the top of a ski slope. The arrows A, B, C, D represent the forces acting on the skier and her skis. Which arrow represents the force pulling the skier up the slope? C, B, A, or D? Okay, so that was really just a matter of common sense. It was D. And then which arrow represents the normal contact force? Now remember that normal contact force, normal meaning right angles, so it had to be C. Again, if you have a quick look at it, diagram, so right angles to D. Okay, remember, has to be at a right angle, so there was a clue in there. The drag lift pulls a skier with a constant resultant force of 300 newtons, a distance of 45 meters. Use the following equation to calculate the work done to pull the skier up the slope. Now, normally in the exam, you'd be expected to remember this equation. Work done is force times distance. However, they're actually quite nice. They give it to you here. So to get this result, what you would have needed to have done was the actual equation, 300 newtons times 45 meters, and then the actual answer, 13,500. Okay, if you just put that answer with no workings, you still get your 2 marks, although you really should show your workings. Okay, but that's the answer, the 2 marks. Okay, on to the next one. At the top of the slope, the skier leaves the drag lift and skis back to the bottom of the slope. Figure 2 shows the velocity of the skier changes with time as the skier moves down the slope. Right, so there's the velocity. So you can see the velocity is increasing, then levels off. Okay, and then you've got time along the bottom. After 50 seconds, the skier starts to slow down. The skier decelerates at a constant rate, coming to a stop in 15 seconds. Draw a line on figure 2 to show the change in velocity. The skier slows down and comes to a stop. So what you should have had was something, it actually gives you a description, a straight line drawn from 13 meters per second down to 0, finishing on the x-axis at 65 seconds. So once again, let's look at the question. There's 50 seconds, and it takes the skier 15 seconds to stop. So you should have thought, right, well, that brings it to 65 seconds, which is there. Constant rate, straight line. So essentially, you should have just drawn a straight line down like that. So if you were actually drawing this, it would have been something along the lines of that. Okay, so you should have something like that in your book, and it's got to be 65. And that would get you 2 marks. So total of 6 for the first question. Toss up your marks and give yourself a score. So question 2, figure 1 shows a spring before and during compression. The arrow F represents one of the 2 forces involved in compressing the spring. There it is. Draw another arrow on figure 1 to represent the second force involved in compressing the spring. Okay, so an arrow drawn vertically downwards from the weight, same length as the given arrow. Now, you don't actually have to name the force, you just have to indicate that force. So it would have been, again, if you want to add an arrow, it would have been essentially the same as that one there, same length. Okay, you can see that. Okay, I can't draw very well, but hopefully you get the idea. Then a student investigated 3 different springs to compare the spring constants. The results of the investigation are shown below. See the spring constants, they're all straight line. You've got the force and you've got the height of the spring in millimeters. Which one of the springs has the smallest spring constant? Okay, now it's C, but that only scores if the reason is chosen, because the smallest force required for the same compression. If you said the steepest gradient, that's not going to get you any marks. The smallest force required for the same compression. So let's look at that. There we go. That has the smallest force required for the same compression. Okay. Oh, sorry, so it's C. Sorry, I was looking at the wrong one. That one, the steepest one. Right. Question 3 shows a child's toy that hangs from a hook in the ceiling. There it is. The child pulls the toy downward and then releases it. The toy oscillates up and down with a frequency of 1.25 hertz. How many times each second will the toy oscillate up and down? Now, frequency is something you're going to be looking at in the next topic, but it is essentially the number of oscillations, basically backwards and forwards every second. So it's basically one oscillation every second is 1 hertz. So you should be able to figure that out by simple process of elimination, be 1.25. Now the next one, again, I put in because you haven't done this yet. Calculate the period of the oscillating toy. Use this physics equation sheet. Now, you haven't been given this and you haven't learned it yet, so I put it in blue for you. This equation is 1 over the frequency, it gives the time period. So you could triangle it up, 1 at the top, frequency and time period at the bottom. So if you do 1 divided by 1.25, you get the time period, which in this case, 1 over 1.25, 0.8 seconds. Now 0.8 seconds scores you your 2 marks. Okay, but if you remember to put in that, you can have it as well, even if you didn't get that answer. Okay, so 1 over 25, and then, sorry, 1 over 1.25 gives you 0.8. Not quite sure where they're getting 25 from. Okay, so when the toy is stationary, its weight causes the length of the spring to increase from 0.05 meters to 0.25 meters. The spring constant is 7. Calculate the elastic potential energy stored in the spring. Now, elastic potential energy, hopefully you remember the equation for this, is half KE squared. Half times the spring constant times the extension squared. Now, that is actually a paper 1 equation. However, because it will be on the equation sheet, as I said, they've stuck it in a paper 2, which is really mean. Okay, but we are going to have a look at it. So, the answer for this one, there's your extension, 0.2 meters. So half times the spring constant, which they gave you, times the extension squared. So 1 mark for getting the extension, 1 mark for remembering the calculation, 1 mark for calculating the elastic potential energy of 0.14 joules. Now 0.14 gets you 3 marks, even if you forgot to put your calculation in. Okay, so question 2 out of 10, give yourself a mark out of 10 for that, please. Question 3, figure 1 shows how atmospheric pressure varies with altitude. So as you can see, the pressure drops the higher you go. Explain why atmospheric pressure decreases with increasing altitude. Okay, air molecules colliding with the surface create pressure, 1 mark, or at increasing altitude, distance between the molecules increases, there's less of them. Or we could say at increasing altitude, there are fewer molecules, so the number of collisions with the surface decreases. Or, so there's always less weight of air than below the surface. Okay, so you've got 3 points you need to make. Air molecules colliding with the surface create pressure. At increasing altitude, there are fewer molecules, so there is less weight of air than below you. Sorry, less weight of air below. Okay, or words to that effect. So have a look at your answer. Have you covered those points? Now, question B. When flying, the pressure inside the cabin of an aircraft is kept at 70 kilopascals, so 70,000 pascals. The aircraft window has an area of 810 centimeters squared. Use data from figure 1 to calculate the resultant force acting on the aircraft window when the aircraft is flying at an altitude of 12 kilometers. Give your answer to 2 significant figures. Now, this is a big question, okay? So, let's look at what we've got. We've got the pressure, we've got the area, we've got the altitude, the height. Okay, so let's go in and have a look. Now, the atmospheric pressure is 20 kilopascals from the graph, and the conversion right, so the area of the window is 810 centimeters squared, but obviously we've got to convert it to meters squared. Now we did do this in one lesson, so you need to convert it to meters squared to be 0.081 meters squared. That's your area. The pressure you need to actually calculate from the graph. Okay, so let's go and have a look at that. So back in. So it says 12 kilometers, so that'd be about there, give or take. And there's your atmospheric pressure, 20 kilopascals there. Okay, so we've got pressure and we've got the area. So hopefully now we have everything we need. Okay, so what we've got is ultimately a force on the windows of 4,100 newtons. The actual answer that comes out for your calculator would be 4,050. So let's just explain how we do that. Okay, so the question is, use data from figure 1 to calculate the resultant force. The aircraft is flying at 12 kilometers. So we did say that we've got 20,000 at 12 kilometers. Okay, but if you look at the answer, okay, we need to actually think this through. It says 5 times 10 to the 4, 50,000. Where on earth are we getting that? Well, let's look at the question. So, the pressure inside is kept at 70,000. You minus the 20,000, and you have 5 times 10 to the 4, 50,000. Okay, so it needed you to spot that and divide that then by the area, which is being converted into meters, and you have your force. So the pressure divided by area gives you the force, and then two significant figures, 4,100. So there was a lot for you to notice in this question. You needed to identify the pressure inside and then minus that from the 20 kilopascals worked out from the graph to give you 5 times 10 to the 4 or 50,000. Divide that by the area, which is being converted into meters. Okay, and then that will give you your force. And then the final mark comes from making it two significant figures. Okay, so from that to that. Okay, so there was a total of 4 marks for that. Okay, question C. Figure 2 shows the cross-section of one type of aircraft window. Explain why the window has been designed to have this shape. Okay, now this was worth 2 marks. The force from the air pressure acting from the inside is bigger than the force acting inwards, so it keeps the window in position. Essentially, the force is pushing, the pressure is higher here than here, so essentially it'll keep the window shape by pushing in that direction, pushing outwards because the pressure is higher. Okay, so give yourself a total of 10 marks, please, or whatever it is you scored for that. Okay, next question. When an object is moving, it is said to have momentum. Define momentum. Okay, so the definition of momentum, a product of mass and velocity. That's essentially what it is, momentum. The next question shows a diagram measuring the velocity of a bullet. So you've got the bullet, which weighs 20 grams, so you need to convert that into kilograms. The mass of the block, 3,980, and then after impact. So it tells you what happens here. The bullet is fired at the wooden block, and the bullet has a velocity of 2 meters per second immediately after impact. The mass of the bullet was 20 grams. Calculate the combined mass of the block and block of wood and the bullet. Okay, so you need to do simple momentum, mass times velocity. So if we apply this, the combined mass was 4 kilograms. And that's just, sorry, I meant force times 2. So mass times velocity gives you momentum. So 4 times the velocity 2 meters per second gives you 8. Okay, so 8 kilograms meters per second. So if you actually go into the answer, 3 marks, you need to do the calculation, 1 mark. The answer is 8, 2 marks, and you must remember your unit for momentum, kilograms meters per second, 3rd mark. Question 3 or 1-3, whatever it is. State the momentum of the bullet immediately before the impact. So what is the momentum of the bullet before the impact? Now, golden rule here, it was this. It was the same, because golden rule, momentum is conserved. So 8 kilograms meters per second. Calculate the velocity of the bullet just before the impact. Right, so you've got to rearrange the equation here. So we know its momentum is 8, and we know its mass was 20 grams, but we've also got to convert that into kilograms. So what we would do, is velocity was 400, that'd be your mark, but you do 8, that's the mass, that's the momentum, divided by 0.02 kilograms, which gives you 400. So the velocity of the bullet was 400 meters per second. And that's worth 3 marks. Question 5. Calculate the kinetic energy of the block of wood and bullet immediately after impact. Now, kinetic energy is another one that appears on your equation sheet, but really is a paper one because it's energy. But because it's on your sheet, here it is. So, half ke squared, so 0.5 times the mass times the velocity squared. So 0.5 times 4 kilograms times 2 squared, because the block and bullet were going at 2 meters a second after impact. So the kinetic energy is 8 joules. So if you do your calculations but get it wrong, you can still have 2 of the marks, but the kinetic energy was 8 joules. And then finally, the question was, the kinetic energy of the bullet before the impact was 1,600 joules. This is much greater than the kinetic energy of the bullet and block just after the impact. What happened to the rest of the energy? Okay, so it was transferred to heat and sound, or does work against the wood, pushing the wood aside or deforming the bullet. So essentially, energy is transferred, and you need to identify that, okay? So that was only worth 1 mark, and you need to say how that energy is identified. So total of 13 marks for that question. Okay, on to question 5. A student investigated how the extension of a spring depends on the force applied to the spring. The diagram shows the spring before and after a force had been applied. So there it is. Complete the following sentences using A, B, C, or D from the diagram. The extension of the spring is the distance between the positions labelled. Right, so for this one, it was B and C. What form of energy is stored in a stretched spring? It is elastic potential. The results from the investigation are plotted on the following graph. So you've got the extension in millimeters against the force. The graph shows the student made an error throughout the investigation. What error has the student made? Okay. They have measured or recorded the length of the spring and not the extension. Okay. Or he's measured between A and C, not B and C. Or the extension does not equal 0 when the force equals 0. So let's have a look at that again. Force should equal 0, so should the extension. Okay, so what they've done is they've measured between A and C. But remember, the spring is already that length. Okay, so that was the reason for that one. Okay, right. Next one, part 2. The student has loaded the spring beyond the limit of proportionality. Mark on the graph the line, the limit of proportionality of the spring, and label that point P, giving the reason for choosing point P. Okay, so there should be a point marked at 5.5 newtons, and up to that point, force and extension are directly proportional, or the line is straight, except past that point, the force and extension are no longer proportional or directly proportional, or the line starts to curve. So you would actually need to mark on your graph at 5.5, which is there, okay, where it starts to curve, okay? You do need to be accurate in the exam. If you didn't mark at 5.5, if you say started marking there at 6, you wouldn't. It starts to curve there, 5.5. Okay, on to the next question. Question C. The student uses a different spring as a spring balance. When the student has a stone from the spring, its extension is 72 millimeters. The spring does not go past the limit of proportionality. Calculate the force exerted by the stone on the spring. Now, you need to remember that spring constant times extension equals force. Now, you've got an extension, 72 millimeters. You've got a spring constant. Now, you'll need to convert 72 millimeters into meters. So let's look at the answer. Where is it? So there's your spring constant times the extension in meters, which is 0.072, 72 millimeters. And so your answer would be 1.8. Okay, so your answer to that should be 1.8. 1.8 on its own, as long as you've done your calculations, gets you marked, but obviously 25 times 72 wouldn't get you the mark because it's 0.072. So you might be out by a factor if you haven't done your conversion again. Okay, so 8 marks for that, please. Right, so question 6. This was about momentum. So we've done this quite recently. A van has a mass of 3,200 kilograms. The diagram shows the van just before and after it collides with the back of a car. The collision, just before the collision, the van was moving at 5 meters a second, car was stationary. Calculate the momentum of the van just before the collision. Show how you worked your answer. Okay, so mass times velocity, essentially. So we know the mass of the van. Okay, 3,200 times 5 meters a second. That's 1 mark for the calculation. And the answer is 16,000 kilograms meters per second. Okay, if you just put that, you can still have your 2 marks. The collision makes the van and car join together. What is the total momentum of the van and the car just after the collision? Right, so let's have a look. We've got the momentum. Now remember, this car is not moving, so its momentum is going to be 0. So if they smash into each other and move off together, this momentum had a momentum of 16,000. This had a momentum of 0. So you simply combine those momentums, which in this case is 16,000 add 0. Which is still 16,000. Then the collision makes. Okay, sorry. Complete the following sentence by drawing lines around the correct answer. So, sorry, that actually should be up there. So the momentum of the cars after the collision is less than. Okay. Is that right? Apologies, I just realised a slight mistake here. This part should actually be up here. So it should say the momentum of the car before the collision is less than the momentum of the car after the collision. Okay, so it should be less than. You know what, we might ignore that one from the final result because I did make a mistake there. Okay, the next one, a seatbelt is one of the safety features of the car. In a collision, wearing a seatbelt reduces the risk of injury. Use the word or phrase in the box to describe the following sentences or complete the following sentences. In a collision, the seatbelt stretches. The time it takes the person held by the seatbelt to lose momentum compared to the person not wearing a seatbelt increases. And then the force on the person's body decreases and so reduces the risk of injury. Right, so actually we'll change this. That one we're going to make out of 5 marks because we're not going to count this one because of the mistake up here. So we'll count that one out of 5 marks, please. Right, question 7. This was about moments. So 2 children, A and B, are sitting on a seesaw as shown in the figure below. The seesaw is balanced. So we've got our distance perpendicular from the pivot and we've got our force. Use the following equation to calculate the moment of child B about the pivot of the seesaw. Now, once again, they've been quite nice here. They've given you the equation. They wouldn't in the exam. So force, 280, times distance, 0.9. Got to do conversion into meters. So 280 times 0.9, the moment was 252. If you got 25200 with no working, you still get 1 mark because you did show that you understand at least how to do the equation. Okay, so part B, use the idea of moments to explain what happens when child B moves close to the pivot. So they move close to the pivot, what is going to happen? Now, 3 marks available here. So the clockwise moment of child B decreases, making it less than the anti-clockwise moment of child A. So child A moves down or child B moves up. Okay, so there are 3 marks. The clockwise moment goes down, so it's less than the anti-clockwise moment of child A, because at the moment they're balanced, or they're no longer, so you could say they're no longer balanced. So child A moves down, or you could say child B moves up, describe that final motion. So 3 marks for that question. So a total of 5 marks for that question. And I think that was the final one. Right, so do 5, 10, 18, 31, 41, 51, 57. Right, so your final score is out of 57, please. Can you send me over your score? I will log that and put that together. I'm actually going to introduce the forces topic on a, sorry, not forces, waves on a different different slide. So I'll upload this and that. So I'll upload that a little bit later as well. Okay, so calculate your score. Obviously, we're going to ignore that 1 mark that was in question 6. So your total is out of 56. Okay, and then I'll come back with a percentage and a grade, hopefully in a few days' time. Okay, thanks everyone.